Okay, so let me bring up my notes. So today we're going to talk about standard library, and then we're going to get into a standard template library, exactly tell you what it is and how they're used. And in the next session, we're going to have the quiz that you have, and we're going to then talk about algorithms and complete the standard template library as we are going through it. The standard library has, let me just bring it up. It has, it's kind of gets spread around specific categories. I'm just going to give you the categories right at the beginning so you kind of know what we are dealing with over here. We have language support. It's in the C standard library, and a new library that goes with memory management, SISD, BADALOG, things like that. So essentially, if you include new, then you're going to switch to exception handling for memory management. We have diagnostics, that is exception handling and standard exceptions. All the exceptions are defined over there, you can see that. General utilities fall into utilities, variant and optional. It handles all the move semantics and optional values that we're going to see later. Strings. We already know what strings are, but string view is what we are going to talk about today. Containers are essentially different representation of arrays when I say arrays, a very, very loose relationship between them. But in C language, we have arrays. In C++, we have vectors, lists, maps, sets, queues, dequeues, lists, forward lists, and all the things like that we're going to go through. Then we have iterators and algorithms, because we don't use arrays in C++ mostly. We use containers. Instead of indexing, what we use some kind of a pointer that is a smart object that acts like a pointer. We call that one an iterator. So iterator is essentially kind of a smart pointer that points to the elements of the containers that we have. And all the operations to move that iterator that points to an element throughout the thing, so you can go to previous and next and jump few elements, go advancing backwards. So you can use still the index operator for all the containers. It's overloaded, but iterators are better things to use. You'll see that later on. You're going to actually use that a lot. Then we have the algorithms, are essentially all the standard and important logics that you have to implement on containers. They are in algorithms like sorting, searching, and things like that. And there are so many things. They're all listed in the notes. You can see what they are. We have numerics. That is the math and numerics. So it's essentially all the math-related functionalities are in there. I/O streams, we have I/O stream and F stream for streaming into and out from files, and F stream. And then we have parallel processing, which is essentially threads and future. We're going to see all those too. So essentially, these are all the tools that we are going to use to implement all the things that we want to do. When I say parallel processing, it means like you write one function and you run five instances of the same function at the same time. So they run parallel. How it happens, it's using threads and async and future. So Um, there's an async over there too, but anyways. So these are the categories of standard library. All right. Having said that, let's move to strings. Okay? We talked about strings and we know what they are. Just as an example to just show what strings are. Strings work like a single variable. This class is created to do text management for you, and it doesn't look like the string as an array. It tries to look at it as a single entity. Of course, you have all the array capabilities of a C string implemented in it, but you can do many things with it that for C strings, you had to include string header file, and you had to pass your array in an unsafe way to a function and then deal with it. With strings, you simply create a string, and most operators that make sense are overloaded for it. So if you plus equal a string, it simply concatenates it. If you plus equal two strings, it concatenates one to the other. So it literally does what plus equal says. You can find out what is a sub. You can extract a piece of the string as a substring, and you don't need to worry about dynamic memory allocation or anything. It does everything behind the scene. You can find a specific piece of token inside a string, and it returns to you the position for it that is of type size t. There is a constant value created in string called npos, essentially null position, which if you have any function in string that returns a position for you, if it's npos, it means it wasn't successful. So that's the way of saying that, hey, I couldn't do what you wanted me to do. I couldn't find what you wanted to find. You can replace a piece of string with something else, remove a piece and insert another piece instead. So you can say, at this position, I want to remove this 5 and put C++ instead. Simple and straightforward. So these are what strings can do. It's much more than that. Please look at the functions and see what you can find in it. Now, you can iterate throughout a string because a string is essentially designed as a container of characters. So you can use a range based loop for it and literally say, I want a reference of a character inside the message. The message is a string, and use good old C two upper versions that are defined in C type and comes with string. When you include that, that is included, and make it uppercase. So anything you do to CH, you're actually doing the characters of the string. So it works exactly like a container, an array of characters, but it's managed and it does everything properly for you. Now, again, please be aware that every like literally you can use like MSG 0 to access all the characters inside the string. There is no problem with that. It is designed to work like an array, but you can do anything you want with it anyways. So it's a very efficient way of working with the string. But you have to realize that behind the scene, what string is essentially a class encapsulating a null terminated, no, it's better to say like this. Let's not specify how it actually handles it. String is a class that encapsulates a dynamic array of characters to represent series of characters for you as a text. Okay? You have to appreciate that, which means If I say over here MSG is equal to ABC, when it sees Seneca is bigger than ABC, it probably it's not going to do any kind of reallocation. But if you put something bigger than Seneca, most likely, not most likely, obviously, it's going to delete the old one and create a new one and so on and so forth. It's going to resize and things like that. So be aware of those things, and having known those things, so in here I'm going to say, we are introducing after C++17 a new class called string view. Now, what a string view is, essentially, it is when you don't need to modify or own a text, you use string view. It is a non-owning, read-only view into an already existing string. So essentially, if I have a string and I want to print it, it's a good idea to pass it to a string view. Because like this, the string view over here is not going to own any string. It's going to point to the data of the str over here. And it does all the things that you need to do queries on the string, and only that, which means you can still have a substring out of it and take something out of it. You can do that, but you cannot modify anything with it. Okay, it's literally a read-only view for a string. Why they created this? Because passing strings, when you read a text or a token or something, you want to pass it around. Most of the time, you use the string to read it, and then you want to traverse through it and dig into it with queries and kind of extract information out of it. You don't want to edit it. If that's the case, then string view is your friend instead of actually using a string. Okay. As I mentioned, with string view, you can actually take pieces and parts of the string and point to those things as you are going through. So you can actually literally have a string view to have pieces of a string dealt with in a separate way. As you see, I can get the substring after the index 11 over here and pass it to a string view tail, and when I show the tail, it's going to only show the Seneca out of that one because that's substring 11. So you don't need to pass as a string over there. Specifically, if you pass it as a string, it's going to actually create a string out of that one, allocate another memory, and so on and so forth. But when you are using a string view, it literally is going to point to the beginning of Seneca over here and view that one only, therefore much faster. And it's going to be much faster and more efficient to use. But the string view has a problem that we need to realize and understand, which is if you pointed to a text, you cannot update that text afterwards and assume that the string view that is pointing to that text will keep the update. Remember, at this moment I'm saying OOP345 rocks and view is pointing to that. Then I'll show the view and it's going to show that. Then I'm going to update the text of the string. When I say view, now take a look at this updated. This is bigger than the other one, right? So it's going to delete the old one. Text is going to delete the old one, reallocate the new one for it. But view is not aware of that because view was set before this thing happened. Therefore, it's going to point to garbage. I cannot tell you what the update over here is, so it's because we literally say it's unpredictable. That's why I have to run it. So when I run this, you will see that it's literally some garbage in it. You see that? It's not going to point to that one. If you want this to update, then you have to, every time you're modifying the text, you have to update the string view too. Even when if it's smaller than that one, even if the dynamic memory, if reallocation did not happen, even if you did not have reallocation, still there is problem. Take a look. That shows that string actually doesn't do null termination because now I'm setting that one, I'm updating the text. It's doing update. When I actually, if I show the text, it's going to show updated. But when I use the view, there is no null termination over there. Again, we call it unpredictable because we are not sure how string is designed. That's the best way to refer to stuff like this. Points to the old data, therefore. The result is unknown. It's extremely important to know that. That's one of the most common mistakes that students make. I'll say careful with string view. Okay. Then we are going to get into standard template library. Now, when we are going to standard template library, we have, in a standard template library, we have the following. This is just an example, okay? And in this example, we have some of the things that I am writing up here. We're gonna spend weeks over these. Okay, so don't think that this is, I'm teaching it now. I'm just showing you where I'm about to go. So we have containers, which are essentially, like for example, this vector. Vector is the most popular STL out there. Like anytime they say, if you are creating an array, use a vector instead. As easy as that, okay? So now I have a vector of integers over here. So that's the container, structures that hold data, vector, list, map, set, whatever. Then we have iterators. Take a look at here. It says nums begin. You see that? So every container, it has a begin and an end query that returns an iterator. The iterator that you see over here, so essentially you are sending the beginning iterator a pointer to the beginning of the array to sort and a pointer to end. End is not 3. It's after 3. Okay? So nums begin is 5. Nums end is after 3. It's not 3 itself. It's after 3. So I'm saying sort from beginning to end. And when you say sort, by default it's ascending. So what it does, it compares the neighboring elements inside the vector and swaps it in the most efficient way possible to sort that thing out and display it. So if this wasn't an integer, it was a student, then you should have overloaded the comparison operators for it. Less than, greater than, equality, and things like that. So the sort knows how to do it. And whatever you design those operators with, that's what's going to be sorted for. So if two students are being compared using their student number, then the sort is going to sort them based on the student number or whatever, right? Obviously, you'll know that sort, if you put a comma over here, accept a third argument that is defaulted and it's not here. And the third argument is a function. Okay? So it's essentially a function object. It can receive a lambda, function object, anything you pass. So if you have a customized comparison thing, you can pass that one to sort. The same thing over here for binary search. So I can say over here, do a binary search from the beginning to the end of nums, see if there's a 3 in it. And it's going to return true if that's the case. So binary search very quickly searches through that thing to see what it is. Vector is the container. Iterators are num begin and num end. We're going to see how to actually create an instance of it. The begin returns an iterate. So if I say auto A is equal to nums begin, A will be an iterator. Okay? We'll see soon. But again, these are iterators. Algorithms is the binary search over here. And object function is not used here. If I added something after sort to tell to sort how to compare the two elements, then that would have been a function object. And that's the entire thing. Everything falls under that category. And you can do everything with all these 4 categories that we have. So STL, example, and categories. Where is it? Now, STL has representation of things that you had before to make it safer. For example, we had unions. What was a union for? A union was for, I don't have a tripod today, so I don't know if I'm going to ask anybody anything. I'm going to, please let me not forget this. Okay, so we had a union. Union was essentially like a class that all the attributes of it shared the same piece of memory. So if you had a union of integer and a double and a float, then all those 3 would have occupied the same piece of memory. Now we have a template for that. So instead of because that's not safe, when you have something like that, if you write something in an integer, then print the double, you're going to have garbage. For that, they create a template, and that template actually works in an extremely awesome way. That template is called a variant. So with a variant, you say, I want a variant of an integer, double, and a string. So it puts all those 3 in the same memory location. Obviously, they all begin at the same memory location. Obviously, a string could be much longer than double if you have too many characters, so many characters in it, right? So what happens over here, the cool thing about a variant is that you set the variant to whatever, it picks the right type to set it to. So when I set my variance to 3.14, the double is going to be set to it. And then I can say get double, and I can print it. Or I can actually set to 345. Now, when I do get string, it's going to show the string. Well, what happens if I do get int now? This is a cool thing about it. You can actually try. You can actually try And if the last thing you set the variant to was not an integer, that's going to throw an exception. So you can safely use it without any problem. So now and that is really an exception, because if your logic doesn't follow the proper procedure and you are, let me put this thing over here, bad access, and now in here I'm going to say cout last setting was not an int in variant v. Okay, so yeah, so that's that. So this is one of the things that is going to come in pretty handy if you ever want to use a union. Use variant instead. Now, that's the variant. Now, let's get into containers. The very first container I want to talk about is called, it's called array, but let me tell you exactly what type of containers we have before we begin. And I'm going to start it with an array, and I'm going to explain those. So first of all, we have an array. Yes. Yes, yes. Variant? Yeah. 2 seconds. Yes, go ahead.
What if in the parameters of the variant, like you don't include double as an option?
And you try to, what do you think the compiler is going to do? If it can cast it to any of those, it will do the closest cast. Okay. So you're going to have an integer being set to 3. Okay, and if it cannot cast it, exception. You're going to have it again, bad variant access. A variant explains exactly why we have STL. The whole reason for STL's existence is to make C++ safe and fast. C++ is very powerful. You can do anything with it. Especially you can shoot your foot and take your leg away. It's not like just shooting the foot. So because it's so open, you can do anything with it. They created this type safe thing right now. So using templates, you are still using C++, and the code written behind it is the most efficient possible thing. But when you're using it, you can actually detect if thing goes wrong. It doesn't make the language perfectly secure, but it's very secure. Okay, if we use, especially as we go higher in the version of the language. Are we good? All right. So an array is literally an array. It's an encapsulation of a C array. And it does that. It is in a stack. Remember, we had 2 types of memory, stack and heap. Stack was at the executable area, so wherever your executable is in there. Very limited. So it's actually in there. It's the exact same size. You cannot change the size. But doing this, you can pass an array from one function to another with absolute no problem. It's going to pass it. It's going to know what is its size. So they added all the features that the array didn't have. So if you want a crappy array, but you want to have it as an object, use an array. But remember what I told you? Whenever you want to use an array, use a vector. Okay? That's the most common thing. Of course, you can know what is its size. You can get what is the front value, what is the next value. You can go through, pass through it. You can create iterators to it. Using iterators, you can pass through. When we get to iterators, you see all the containers work with iterators. So because we don't know what they are, we're going like this, but they work exactly like an array. I can do a range. I could literally write a regular loop over here instead of writing something like that. I could literally write over here for come on, size ti set to 0 and I less than nums dot size and I plus plus. I could do cout nums I. So you can use the old-fashioned type of thing with it. It works perfectly. There's absolutely no reason not to use this, but you can use range-based loop and stuff like that if you want. Make good? Be good? Now, let's bring it up. We have 3 types of container, okay? We have sequential container. Arrays, vectors, queues, lists, forward lists, things that are sequential. It goes from one to the next, okay? Like the seats that we have over here, sequential. When you have stuff like that, that's the one. Then we have container adapters, which is essentially a wrapper. When I say, first of all, what is the meaning of wrapper? Anybody knows? Not wrapper, I mean like wrapping, you know? Like, not like M&M. I mean, like, what a wrapper is. Anybody knows what's a wrapper? Online people, do you know what a wrapper is? Do we have anybody online, or I'm talking to myself?
It has the features of
I know, it's very small, but it's much. Go ahead.
It has the features of the thing that it wraps, but also it has another feature on top of it.
Yeah. So what is the when we say wraps? What does it mean? Do you know what does it mean when we say wraps? Wraps essentially means encapsulate. So if I remember I created an int thingy over there. I created an int for my examples. That was a wrapper. That was a wrapper class around an integer, so it can not add features. It added features, but also it limits too. Okay, so container adapters are actually limiters. They limits the features of, for example, a list, and it creates a stack out of it. What is a stack? It's a standard data structure algorithm that you have to apply to certain things. A stack is last in, first out. It's like a stack of plates in the kitchen. You always pick up the plate that you put on last. The one that is first, if I have 20 plates and there are only 3 people in the house, probably the last one never gets touched unless I have a party, right? So that's what stack is. That's for that type of a design. So we can use a vector as a stack. But if I do it, then I can do something that stack is not supposed to do. And all these data structures are there to force you use a logic that fits the implementation of the problem. So if a stack is needed, then you use a stack. And that stack wraps one of these containers to only allow you to use specific features of the container. And then we have associative containers that essentially it organizes the data. So what happens is that, like, for example, a set is a container that you cannot put repetitive stuff in it. If anything's duplicated, it's just going to just ignore it. It's not going to add it. You'll see what I mean. Or map and thing. We're going to go through that. Okay, so let's begin. Array and types of containers. Next one, the most popular, is vector.
Can we put stack in a vector?
Pardon me?
Can we put stack in a vector?
Can we put a stack in what?
In a vector.
Why not? A vector of stacks? Of course. Can you create an array of arrays? Yes. So I got goosebumps with what it says, what you said. Like that's programming. When you're doing object-oriented program, anything is an object, even a container. So you can have a container of containers, nobody's going to stop you. And as a matter of fact, you need to do that many, many times. Okay? So, vector. I'm creating a string of a vector of strings. And what is interesting about vectors is that the features that it has, it essentially first of all, vector is created in a contiguous way, which means the data that vector is using, it's going to be exactly one array. So it literally wraps an array, but resizes it and uses it in a most efficient way. Okay? Because of the fact that it's actually using an array behind the scene to do something, then vector is good for fast random access. If you want to jump to the next element and come back and go back and forth inside, because you can literally use an index operator with a vector and instantaneously jump between elements very quickly. And also, it resizes it automatically. So it's efficient to push back stuff on it. You can push front, but if you push front, then it's going to be inefficient. You'll see soon. So essentially, I can push back stuff, essentially add stuff at the end. So as you see over here, I am pushing Daniel at the end. Then in here, I'm going through a range-based loop and go through. So each S over here is going to be a string, and it's going to go through it. I can insert. So as you see over here, students begin is returning an iterator. Plus is overloaded with the iterator. When you add an integer to it, it means go that many further. One further, it means one, go one after. So I'm essentially saying insert Eve after the beginning. As simple as that. Or I can say erase 3 after beginning, and it erases. And I can say pop back, it means take the last one out. Yeah, so that's what it is. It has many functions in it. Please go through it. They're all listed. I cannot give you example of every single thing. It's going to take forever. It is listed over there. And if it's not listed in the notes, all you need to do is find where the mouse is and then go students dot assign back begin capacity and in place back empty get out. So all the things that you see, all the like shrink to fit, it has many things like shrink. So what stack does, essentially what vector does is when it's actually working, if you create a vector of 20 integers and use only 5 of them. So you created a vector of 20 integers and you just pushed back 3 things in it. You can say shrink to fit, so it reduces the memory and resizes that to that one. It has many functionalities to use, but all you need to do, all you need to know is that it's using an array to implement everything. And because you have already done this, you know what are the implications. You know what you can do to be fast and what you can do with a vector that's going to make it slow. So you don't create a vector of one element and keep pushing back. That's going to be expensive. If you are doing something like, if you are creating a vector that you think it's going to be 100 things, you make 100. Now, if it gets bigger, it gets reallocated twice. Okay, and when you're done, you can shrink it to fit, and so on and so forth, as what you did with dynamic memory allocation. But again, as I said, at any moment you want to use an array, use a vector. And in all your assignments and stuff, please. Okay? So the next one is a DQ. So DQ is, it does fast insertion and removals on both ends. Okay? It does fast insertions and removals on both ends. But it's not contiguous. It manages its own memory the way it finds fit. Therefore, the random access for it is not available. You should not do that. It's good for sliding windows. You know what the sliding window programming is? Sliding window is when you have series of data and you have a window of visibility and you slide over that window to only see a portion of that data. A sliding window is the text editor when you scroll up and down. The menu, the radio, what's that? A menu that you open and you slide up and down. History that you have in your browser is the sliding window. So a DQ is something good for that. You can insert and remove stuff easily. You can browse and go forward and backward relatively fast, but jumping from first element to 50th and back to 3, and that's slow. So you shouldn't do that. Okay. Now we're going to go to list. A list is literally a doubly linked list. It is literally a doubly linked list. And what is a doubly linked list? This is a doubly linked list. A doubly linked list has many different implementations in data structures. I'm just giving you one of them, okay? So this is a doubly linked list, okay? It has a pointer in it. That pointer is a pointer to what we call a node. A node is essentially a class, an object that holds the data of a doubly linked list, of a linked list. Now, for a doubly linked list, the nodes are configured like this. So this is one node. Oh, that's not a node. One node here. One node here. another one here, another one here. As you see, the data, they are everywhere. The big thing in the middle is where the data is going to sit. The small ones at left and right are pointers to nodes. So I have 4 nodes over here. Each one is a pointer to a node. And each node is aware of who is next. And as you see, in no way it's ordered in memory. And which one is the last. So it says next, you can come to this one. Next, you go to this one. Next, go to the next one. And then you hit the wall, you stop. And with the AA linked list, you can go backwards. So each node knows who's the previous until you hit the wall. And the object itself has access to the linked list. It can go back and forth in it. Okay? Because of the nature that it has, it is extremely expensive to do random access. If I told to a linked list to go, now the linked list, sometimes they are made more efficient by creating a pointer to a beginning, to the beginning, and a pointer to the end, which essentially continuously point to the very first and very last, okay? And so if I wanted to say go to the 5th one, I have to go jump to the first one, then count 1, 2, 3, 4, 5. And if it's so it is impossible for me to go from one node to another in one instant. I have to always go through next until I hit it. And the only way that I know what is the sequence number of this node is if I actually added the sequence number inside the node, which is a bad thing to do because this linked list is designed for insertion and removal. If you want to insert a new node here, there is no need for shifting or any fuss like that. Just add the node and make the node points to where you want it to be after and where you want it to be before. And remove the connections so the other one looks at it like this. And these 2 connections are gone. So in an instant, you can add something between now in the index 1 and 2. I just inserted something in the middle without adding anything. And if you want to remove one, it's as simple as that. All you need to do is to sever the connections and delete the node. Everything goes back to what it was. So that's why AA linked list, each node knows who is previous and who's next. And it has no random access, which means index operator is not even overloaded for it. You cannot use index operator for this. And also, it is best for frequent insertions and removals. Okay? And you can push back, push front, insert. Now you will see actually an iterator being used actually. So I'm saying iterator numbers begin. This is pointing to the beginning of the list of integers. Now I can say advance twice forward, which means it's got to go 1 and 2. It comes to here. Now the iterators point to the second one. Okay? Now I can say insert after this iterator 25, so it's going to insert it between the 2. Now I'm going to say I can use a range base to do the exact same thing, or I could have used the iterator for it. It doesn't make any difference. So I could literally use the iterator for it, and we're going to come to it, and you'll see it soon. But iterators are being used for this the most. We are not using any indexing and range-based loops. So this is a double A linked list. And this is called a list. Okay, so the list is essentially a double A linked list. So and then we have something that is even more lightweight than this, which is called a forward list. Now, a forward list is even weaker than this, which means remove all the back ones, which means each node is only aware of the one in front, which means there is no way back. Let me quickly see if I can draw it. So this is not a double linked list anymore. This is a linked list, pure linked list. And the nodes in here, they only have data and next. Data and next, data and next. And one points to next, next, and the last one is null. Oops. Is null. And that one points to the first one. Okay, and obviously it has another one that deals with the current one. So this is pointing to here, or you can set an iterator to point to this one, and then an iterator can go can go forward, but you can never come back. If you want to come back, you have to set it to the first and then keep going. Okay, so this is what we call a forward list. It saves memory because it has one pointer per node. Now with double linked lists, if you are holding characters, it's going to be very expensive because for each character you are using 16 bytes for pointers for next and previous. But if what you're using is a huge class, then it's worth it. Okay? So again, depending on what the data structure needs, that's what you're going to use. Okay, so that's a forward list. And with that, we're going to go to the container adapters. So container adapters are essentially, as I told you, they are wrappers around what we had before. And the simplest one is essentially a stack. It only has a push and pop and empty. That's it. You can push stuff in a stack. You can add entities to a stack. You can remove entities from a stack, and you can see if it's empty or not. That's it. It's a stack. If we didn't have stack, we didn't have function calls. Every single function call that you do, at the moment that it's calling a function, it pushes that address that the function call is being made into a stack. So when you have 10 function calls back to back, 10 addresses of the function calls are pushed into a stack. Return of a function call is a pop. So when it gets to the return, it pops. When it pops the address where it came from, so it knows where to go back to and continue. So as your program executes, that's why they call it stack for the heap and stack, because it's implemented as a stack. So as your program executes, the stack grows and shrinks and grows and shrinks and grows and shrinks. When it reaches to return of main, the last thing is popped and the stack is empty and your program is clean. But if your program ends and there's still something in a stack, that means you had boo-boos. It should never happen. That's usually, that's when you do an abort instead of an exit. Remember what abort was, right? So that's a stack. I have the code for the stack. I've written it for, previously when I was teaching these things, to teach this part, I would actually start coding a stack from scratch using C knowledge. And then I would tell you, you don't need to use it because there's a stack. But as the time goes forward, students are getting less interested into behind the scenes stuff and they want to see how to use the tools. That's why I'm moving towards showing you what they are. But I can provide you the code if you want, so you can take a look at it and see what it is. So that's that. And the next one is called the queue. Queue is essentially Tim Horton's lineup. Okay? So a stack, the first one you push in is the last one that is coming out, right? In a queue, the first one that goes in is the first one that comes out. So when you get into lineup, if you're the first one, you're going to be the first one to go out. It's a fair queue. It comes from one side and goes to another. And that's, so again, every push, it pushes to the stack and it pops it's first in, first out. The other one is first in, last out. This one is first in, first out. And this is called a queue. Now we have another type. Yes, go ahead.
Why did they use stack on the function calls? Like
There's no other way.
other way?
It's impossible.
Okay. So
Again, when I did the stack, I actually went through a program and I walked through it and I drew this stack on the thing. So think about it. Let's put it like this. So you have a function call at line 4. Let's call it line instead of address. And you have a function call, the same function, at line 10. Okay? So when the function is called at line 4, it pushes 4 into the stack. Okay? And the function ends, it pops. What comes up? 4. Because that was the last thing that was popped. So it knows that the execution from the function should go back to the line 4 of the caller function. Correct? Now let's say I have the function foo called as line 4. Okay? And then I have function fa inside foo called as line 20. So when foo is called, 4 is pushed. When fa is called, 20 is pushed in there. 20 of foo. So when function fa ends, it pops. What comes up? The last one that was in. Therefore, it knows it has to go back into foo, not somewhere else, and continue the execution. So each function call is literally a push, and each return is literally a pop. Otherwise, the CPU could not keep track of how the execution is going to happen. It's literally impossible. There's no other way to do it. Hopefully you're going to go to university and you do compiler design and things like that, and then you'll see that when you write a compiler, how actually it's called. It's literally you're pushing when a function is called. So essentially what you push, and then you push the arguments into another stack for the arguments. And when it goes to the function, it pops. So what is just being passed to the function will pop out. And that's why C language receives the arguments in reverse order. This is something that we learn in advanced C. So if you have 3 arguments A, B, C, if the arguments that you are using, let's say in the first one I have A, okay, I'm doing a function call. So my function receives 3 integers. The first one is A. The second one is A plus equal 1, The third one is a plus equal 2. If the value of a is there, I would think that 1 will go to the first one. Because it's 1, I added 1 to it. 2 will go to the third, and 3 will go to the second one, right? But that's not the case. Because when it's pushed in, it pops back in reverse. The last one gets evaluated first. These are very high-tech, detailed thingy that you need to know about the language. And those things that people try to find bugs, they cannot find the bug. And they say, what the heck is going on? So like a function called like this, if I have void foo, and then I have a function called over here like integer value is equal to 10. Then I write over here foo v comma v plus equal 5. You would think that 10 and 15 is going to go to the function, right? But what's going to go in it is 15 and 15. Why? Because when the arguments are passed to foo, they are pushed into a stack. So first v is pushed, then v plus 5 is pushed. Then for when it pops, it evaluates, it becomes 15, therefore v is now 15. So the second pop is 15 now. So these are the things that when you write a compiler, you know what's going on behind the scenes. So these are the things. That's when I say if we didn't have a stack, we couldn't call a function. I wasn't joking. You really, like, there is no other mechanism that can handle it. Okay? So that's that. So that's Q. No, this is nothing. That's string, okay? And the next thing is what we call a priority queue. Now, a priority queue's job is to always keep the largest value at the top of the thing. So when you create a priority queue, push 10, you push 40, you push 20. When you pop, what comes out is 40. The very first one, it's a queue, but it always keeps the highest one at the head of the list. What is this thing good for? Priority jobs. Like, for example, you are writing a program to board the passengers into an airplane. And you have a type that you have a type of passenger. And the comparison between passengers is done with the type. So you overload the passenger to be compared by its type. So we say one type is infant or senior. That's priority 1. Then you have first class. Then you have business class. So what happens is that when you are adding the passengers, priority queue will automatically sort it in a way that the highest priority stays at the head of the queue and it goes back to the lowest priority. And that's what happens. So that's what, again, these are all wrappers. So essentially this, so to tell you exactly, let me just, so this is priority queue. And stack is a wraparound DQ. Queue is a wraparound DQ. Priority queue is a wraparound vector. So they implemented priority queue with the vector because it has insertion and stuff. Yeah, so now we're going to go into iterators and see what the iterators are, and then after that, I think we're done. Oh, no. Set. I forgot. The associative containers. Very important. So with a set, when you are inserting, it will insert always sorted. So it doesn't matter what you set, it will always be sorted. That's number one. So no matter what. And how does it compare? Using the comparison functions, okay? That we're gonna see, comparison operators, okay? So as you are putting stuff in a set, you put 30, 10, 20, it ignores it and makes it 10, 20, 30, okay? If you insert 25, it's gonna be between 20 and 30. It's gonna be automatically there. If you insert 10 again, it silently ignores it. It doesn't even care if you inserted it or not, okay? And you can find stuff extremely quickly over there. So if you try to find, it returns an iterator to what it finds. So essentially, if you want, the reason that it returns an iterator to what it finds instead of returning an index, it's because there is no index in here. It's sorted, so nothing goes with the same index that it was in it. So what you do, if you create a student number and you compare the students using operator overload with student numbers, then you can simply put them all in a set. Automatically they're going to be sorted in the thing based on their student number, and then you can simply do find on a student number, and the iterator it returns, it's either the student with all these information or numbers n if it doesn't find it. Just imagine, if I give you a program, this could be one like your midterms test. I'll tell you, read the names of the students and their student number in this class, and I'm going to have a class created, and I'm going to say, use a container to do a quick search in the students that you're reading from a file using whatever. Okay, so you literally read the stuff from the file, put it in there, you just do the comparison operators less than, greater than, equal, and you pass the student number, so you put everything in a set, you simply do a find with the student number, and if it gives you back, you have the student, if not, so literally that much line of code, very, very quickly can be written. So there is no search mechanisms needed to be written. Although we have an algorithm for it, we have STL algorithms for this that we're going to learn soon, but this STL has its functionality for it. That it's extremely fast, actually. It's implemented over binary tree that is beyond too rich for our blood. When you study DSA, you know what I mean. So it's literally a binary tree. So that's the set. And last but not least, that I love, I use it so many times. All the configuration file that you have for your submitter program that actually does the configuration for this is written with this container that I'm going to show you. So let me know P, Q, Q's. So you have, imagine that you have paired values, key and value. For my case, for my configuration files, I had a configuration like, for example, assignment name. And I want to know what the name of the assignment is, workshop 1, something like that. Or I have who is submitting this program, like submission name, and then the name of the student comes up. Or due date, and I have 5 different due dates over there. And I want to have these things in something, so when I actually want to get the due date, I quickly put due date and it gives me back. What do I do for that? I use what we call map. It's a beautiful thing. So you create it like this. You say map string in. Now this could be any class, this could be any class. Okay? So string and int, the phone book I'm putting over here, And this is how you add it. You literally put some value and you say equal to some another value. It inserts the string into the first one and the value into the second one. Later, if you print phone book Alice, 1, 2, 3, 4 will be printed. So it literally is a dictionary. You create a dictionary. And that's it. So, yeah. So as you see, yeah, and you have, and you can see exactly what is that entry, like what is the first and what is the second. So when you, if you go through the entries in the book, first is of type string and it returns that one. Second is of type integer and it returns the second one. That container is called a map. Very useful. Element O. Oh, I didn't put P. So this is supposed to be, did I put P? No. That's P. And this is Q map. And now iterators. Very simple and straightforward. Every single container has an iterator class in it. So if you want to create this iterator to point to the element of that container, you must instantiate the iterator from within that container. So I can say for vector int iterator it equals to numbers begin. So by creating vector int iterator it, I am creating an iterator for any vector of type integer. So this is the class that is defined inside vector int. If it was, I don't know, what should we call it? A set of employees, then I had to say set employee iterator I. Okay, so you literally create the iterator from within whatever container you have, and that is capable of pointing to any element of that one. Usually we start from begin. Okay, so now it's begin. Now I'm going to say why it's not end. Plus plus is overloaded for it. If you go plus plus before or after, if you do it, it means go to next element. And we have so many functions that we can use with iterator I'm going to tell you, but like advanced, for example. You can say advanced, so you can, there is a helper function called advanced. You put an iterator and then you put 5. It means from this iterator advance 5 steps forward into that. Or you can just write auto. Okay? And the asterisk is overloaded for it. So it dereferences. So IT becomes the iterator, but when you put the dereferencing over there, it tells what is the class itself that is pointing to. IT is the iterator, target of IT is the element. Exactly like a pointer. Now, as you see, when you do iterator, you can go backwards. So you can actually set the iterator to end, then you go minus, minus, and you keep coming back, right? If you don't want to do that, if you want to advance from the end to the beginning, Q, R. You can do a reverse iterator. What is a reverse iterator? It literally reverses the iterator, exactly as I mentioned. So if I create it to R begin, if it's R begin, it's actually the end. And I can check it what it's not R end. R end is 1 before the first. So when I do plus plus, I literally go from the end to the beginning. You can reverse the traverse of the iterators if you want to. Last but not least, oh, did I save it? Control. What if you pass a container as constant reference to someplace and you want to use it? And iterator is read-write. If you want to extract the iterator from a constant thing, then it won't be able to do it. Or what if you want to pass an iterator to a function and you want to pass it as a read-only iterator so it doesn't? For that, we have constant iterators. And I'll show it to you. Either you can use a constant iterator to create an iterator that is read-only. Either you can use a constant iterator to create an iterator that is read-only, or if your container is a constant reference and you want to extract the iterator that is constant, you can use cbegin or cend. Cbegin returns an iterator that is read-only, that is constant. So I could put set int constant iterator id is equal to cbegin over here, or just put out of this it becomes constant. Are we okay? So these are constant iterators. And I could tell you the utilities. I'm just going to show you the utilities that we have for iterators so you can actually see. No. I'm going to talk about these after I tell you what the helper functions that I told you and the iterator utility functions are more understandable when we know the algorithms. Okay? So I'm not going to mention them now. For now, use the iterators as they are. When we cover the algorithms, then I'm going to tell you the utilities that you can apply for iterators so you can pass the iterators to logics properly to behave the way you want it to behave. Okay? That's that. Questions? Lots of information, okay? Please, I wrote small little examples so you can open one of them freely, focus on that, and start fiddling with it. I beg you, for all the people who are listening online, and the 4 of you who are here, to please go through these notes, open them up one by one, play with it, break it, see what works, what doesn't, and learn how to work with it, okay? I wrote small little things, so it's not too complicated. You can just, yeah, please do so. Pass them around using functions and things and see what happens. People online, how are we doing?
We're good.
All right. Okay, thank you very much. This is it. I'm going to post it right now, and since I have time, I'm going to save. And after posting this, I'm going to actually upload the video right now because I can. Okay, it's gone. All right.